Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from indefinite integrals, right? So here we have a problem, that is if the integral of 1 over cos x raised to power 6 plus sin x raised to power 6 is equal to tan inverse lambda times tan 2x plus c, then we have to find the value of lambda, right, where lambda belongs to the set of real numbers, right? So here we see that we have this integral, right? And what we will do here, we'll try to solve this integral, and after getting the result for this integral, we can compare that result with this one, right? And after comparison, we can easily find out the value of lambda, right? So let us start. So first of all, let us take this integral as I. So I is dx over cos raised to 6x plus sine raised to 6x, and here we see that in the denominator we have cos raised to 6x plus sine raised to 6x. Now let us first simplify this expression using some simple algebra. Now here we can write cos raised to 6x as cos square x power 3. Then similarly we can write sine square x raised to 3, right? And now we have this form, that is a cube plus b cube, where a is equal to cos square x and b is equal to sine square x, right? Now we know that the formula for a cube plus b cube, that is a plus b, a square minus ab plus b square, right? So a cube plus b cube can be factorized like this, and a plus b is simply equal to 1, because a is cos square x, b is sine square x, and that is equal to 1, right? So this is a very famous identity in trigonometry. So cos square x plus sine square x is 1, so a plus b is equal to 1, and here we have a square minus ab plus b square, right? Okay, so we have a square minus ab plus b square. Now let us first calculate the value of a square plus b square. Now a square plus b square is equal to, we can write a square plus b square as a plus b whole square minus 2ab, right? And we have just calculated that a plus b is 1, that is cos square x plus sine square x is 1. So here we have 1 square, and here we have minus 2ab, right? So what we will do, we have a square plus b square is equal to 1 minus 2ab. So here we'll substitute this value. So we have 1 minus 2ab plus minus ab, right? So this is 1 minus 3 times ab, right? And now we can substitute the value of a and b over here. So we have 1 minus cos square 3 times cos square x and sine square x, right? So for cos 6x plus sine 6x, we have 1 minus 3 times cos square x times sine square x. So now let us write our integral I as dx over, for this value we have this expression. So we have 1 minus 3 cos square x sine square x, right? Okay, now in order to calculate or compute this integral, what we will do, we'll divide the numerator and denominator by cos raised to 4x, right? So we'll divide the numerator and denominator by the power of cos x, which is 4, right? So what we will get here, we have 1 over cos raised to 4x, and then here we have dx, and we have 1 over cos raised to 4. Then here we have 3 cos square x, then we have sine square x divided by cos raised to 4x, right? So now let us simplify this integral. So we have I is equal to, see, 1 over cos x is equal to secant x. So we can write here sec raised to 4 x dx divided by, here we have sec raised to 4x minus, and here cos square x, the two terms, that is cos square x, get cancelled. So here we are left with simply cos square x, and sine square x over cos square x is tan square x, right? So here we have 3 times tan square x, right? Okay, now at this step we'll make use of one important identity from trigonometry, that is 1 plus tan square x is equal to secant square x, right? And if we square both sides, what we will get, we will have 1 plus tan square x raised to power 2, and here we have sec raised to 4x, right? So here we'll substitute this value, and sec raised to 4x can be written as secant square x times secant square x dx, right? So we'll split sec raised to 4x as sec square x, sec square x, and here we have 1 plus tan square x whole square, and here we have minus 3 tan square x, right? Now in order to proceed further, here we'll make use of the method of substitution, right? So what we will do, we'll take u is equal to tan x, right? So when u is equal to tan x, then du over dx is equal to secant square x, because the derivative of tan x is sec square x, and du is equal to sec square x dx. So here we'll have du, and for sec square x we have this identity, that is 1 plus tan square x, right? So now we can write, see, for sec square x we have 1 plus tan square x, and tan x is equal to u, so we have 1 plus u square, and here we have du, and in the denominator we have 1 plus u square raised to whole square, and then we have minus 3 u square, right? Now let us simplify it. So we have 1 plus u square du divided by, we can expand 1 plus u square whole square by a plus b whole square identity. So we have 1 plus u raised to 4 plus 2u square minus 3u square, right? And this is equal to 1 plus u square du divided by, here we have 1, then we have u raised to 4, and 2u square minus 3u square is minus u square, right? Now in order to proceed further, what we will do here, see, we have 1 plus u square over 1 plus u raised to 4 minus u square, will divide the numerator and denominator by u square, right? So what we will have, I is equal to integral 1 plus u square over u square, and in the denominator we have 1 plus u raised to 4 minus u square divided by u square, right? So now we can simplify it. So we have we can split here. So we have 1 over u square, writing this term as a sum of two terms, and here we have 1, so we have 1 plus 1 over u square du divided by here we have 1 over u square, and then u raised to 4 over u square is u square, and u square get cancelled, so we have minus 1, right? Now here in order to solve it further, we'll make one more substitution here. So we'll take, say, t is equal to u minus 1 over u, right? So why we are taking this substitution? Because the derivative of t with respect to u is 1 minus that is minus 1 over u square, because the derivative of 1 over u is minus 1 over u square. So we are left with 1 plus 1 over u square, right? So now dt can be written as 1 plus 1 over u square, and here we have du, right? So for this term we can substitute dt. That's why we have taken this substitution, that is t is equal to u minus 1 over u, right? Okay, now let us come to the denominator. See, here we have 1 over u square plus u square minus 1. So what we will do, we can square both sides. So we have t square, and here we have u minus 1 over u whole square, and expanding this term with the help of a minus b square, we have t square is equal to u square plus 1 over u square minus 2, right? And u square plus 1 over u square can be written as t square plus 2, right? So taking this negative 2 to the left hand side, so we have u square plus 1 over u square. So for this term, that is 1 over u square plus u square, we can write t square plus 2. So now this integral becomes dt over here we have t square plus 2, and here we have minus 1. So we have integral dt over t square plus 1, right? So t square plus 1 can be written as t square plus 1 square, and we know that if we have the integral dx over x square plus a square, then the integral is equal to 1 over a tan inverse x over a, right? So here for x we have t, for a we have 1, so we have 1 over 1 tan inverse t over 1, right? So we can write it as tan inverse t, and here we have the constant of integration as c, right? So we have tan inverse t plus c, and t can be replaced by u minus 1 over u. So we have tan inverse u minus 1 over u plus c, right? So viewers, we have obtained the value of the integral I as tan inverse u minus 1 over u, and our u was tan of x, right? So here we'll take u is equal to tan x. So we have tan x minus 1 over tan x and plus c, right? C is the constant of integration. So we can now write tan inverse, and here tan x minus 1 over tan x, so we can write it as tan square x minus 1 over tan x, right? And plus c. So now we have the expression for our integral I as tan inverse tan square x minus 1 over tan x plus c, right? So at this step we'll make use of an important result from trigonometry, that is for tan 2x, right? So why we are simplifying this expression further? Because we have to reach at this step, right? See, here we have tan inverse, here also we have tan inverse, but here we have tan square x minus 1 over tan x. So we have to simplify this term, right? So tan 2x is equal to 2 tan x divided by 1 minus tan square x, right? So why we are using an expression for tan 2x? Because see, this expression is similar to this one, right? So we can now write tan 2x divided by 2, taking this 2 to the denominator of tan 2x. So we have tan x divided by 1 minus tan square x. So here we can take negative sign outside because here we have tan square x minus 1. So we can write tan square x minus 1, right? So now we have minus of tan 2x divided by 2 is equal to tan x divided by tan square x minus 1, right? Now if we take the reciprocal, then we have 2 over minus tan 2x is equal to tan square x minus 1 over tan x, and for tan square x minus 1 over tan x we can substitute 2 over minus tan 2x, right, over here. So now I can be written as tan inverse, and we have minus 2 over tan 2x plus c, right? Okay, so now we have obtained this result, and still this result is not similar to this one. So what we will do, we'll again simplify this expression by making use of an important result from inverse trigonometric functions. Now let us use an important result from inverse trigonometric functions, right? See, here we have the value of integral I as tan inverse minus 2 over tan 2x plus c, and we have to reach at this expression, right? So here what we will do, we'll make use of a result, that is tan inverse of x is equal to cot inverse of 1 over x minus pi whenever x is less than 0, right? So here we have tan inverse x. So here for x we have this term, that is minus 2 over tan 2x, and this term being a negative sign, here this term is less than 0. So now I can be written as cot inverse 1 over x. So we have 1 over minus 2 over tan 2x, and here we have minus pi. So we can now write it as cot inverse of tan 2x divided by minus 2 and minus pi. Here we have the constant of integration also, right? So we have now I is equal to cot inverse tan 2x over minus 2 minus pi plus c. Now here we see that pi is a constant, right, and c is also a constant because c is a constant of integration and pi is also a constant. So we can replace minus pi plus c by some other constant, say c1, right? So now I can be written as cot inverse, and we have minus of tan 2x divided by 2 plus c1, right? Okay, now we have obtained this expression. Now this expression is not still similar to this one. So what we will do, we'll make use of one more important result from trigonometry, right? And the result is cot inverse of minus x, right? Cot inverse of minus x can be written as pi minus cot inverse of x, right? So now I can be written as using this result, cot inverse of minus x is equal to pi minus cot inverse of x. So for x we have this term, so we can write pi minus cot inverse of tan 2x over 2, right? And c1 is the constant of integration, right? Okay, now here we have the expression for I as pi minus cot inverse tan 2x over 2, but we have to reach at this point, right, or this expression. So what we will do, here again we'll make use of one more identity from inverse trigonometric functions, and that is tan inverse x plus cot inverse x is equal to pi over 2, and cot inverse x can be written as pi by 2 minus tan inverse x, right? So for here I can be written as pi minus, for cot inverse x we can write this expression, so we have pi by 2 minus tan inverse of tan 2x divided by 2 and plus c1, right? Now we can simplify it, so we have pi minus pi by 2 plus tan inverse tan 2x divided by 2 plus c1, right? And I is equal to pi minus pi by 2 is pi by 2 plus tan inverse tan 2x over 2 plus c1, right? And pi by 2 plus c1 is again some constant, say c2, right? So I is equal to tan inverse of half tan 2x plus c2, right? And now if we compare this result, that is tan inverse of lambda tan 2x plus c2 and c are the same constants, so here we can also replace c2 by c. So if we compare these two expressions, then we get lambda is equal to half, right? So viewers, when this integral is equal to this expression, then the value of lambda is equal to half.